All right. Thank you for coming to my session today. I'm Karl Weinmeister. I'm with Google's developer advocacy team. I manage a team of data scientists that go around the world talking about data science and helping people understand it. I'm actually based out of Austin and glad to be here in Dallas today. So my talk is going to be 20 minutes, pretty brief, kind of covering the different entry points into machine learning. You know, it's a complex topic. You can study it for years, but you can also start using it pretty easily, and there's different entry points for you. So we're going to go over everything from APIs to AutoML, that's a new technology to build models without code, to custom models. At the end, I'm going to do a brief demo, and that I'll actually have to go over to the podium for that. But anyway, let's jump right in. As I mentioned, kind of walking through some concepts. I know for experienced data scientists, it might not be anything new, but it'll help level set people on what we're going to talk about. We'll talk about APIs, AutoML, the Cloud AI platform from Google. It just happens to be how we can implement some of these ideas, but these ideas can be implemented on all kinds of environments. And TensorFlow, our open source framework for implementing machine learning. So when people think about some of the cool stuff happening in AI at Google, they might think about you know, the home assistants that you can talk to, or self-driving cars, or game strategies. But there are a lot of technologies that have been using machine learning for years. So things like in Gmail, you might see like responses that are kind of crafted automatically to different emails that you receive, or you might see in Google Photos, image recognition technology. So what Google's been doing is taking all of that great technology we've been using in-house and surfacing it and enabling the public to use it and providing open source frameworks using it. So let's do a quick introduction to what machine learning is. Essentially, it's just finding patterns in data. And there are several different use cases for that. These are just a few. Recommendations, you know, trying to figure out, you know, the best movie or TV series or product. Forecasting, you know, what is something going to be like in the future. Game strategy, or classification. We're going to talk about classification today. Classification is essentially just putting things into the right bucket, applying the right label to it. Is this a cat or is this a dog? So let's talk about building a model. What do you need to do with that? First, you need data, lots of data, and labeled data. This is the training process. You need to know what's the right answer. So that's what you do in training. You have a data set with examples that are labeled. You take that training data, you apply a machine learning model to it, or algorithm to it, and you get a model. That's what it is. But it requires data. What if you don't have any data? What do you do? You can use Google's models. We have pre-trained APIs for a variety of different domains, things from natural language to video to natural language, all kinds of different things. So let's look at a couple examples of that. So here's the Vision API. So if you have any image data, you can just use this without any training whatsoever. So here's kind of a fun example. This is an amusement park called Luna Park. And you know, we fed that into the API. And this is actually available on the website, all of the different APIs you can demo yourself. So just go there, upload an image, see what you get. So in this case, you know, you see it's a landmark, a place of worship, okay? You know, a couple other things, amusement park. And you know, it's kind of a different looking structure. I wanted to kind of give it a challenging problem. If it identifies a person, it can give you additional metadata, things like what emotions is it seeing in the person. So kind of a poker face here, except for the headwear. It thinks that there's headwear is very likely, so that kind of crown thing it figures out. It can also do OCR, so any text in the picture it'll pull out. And then kind of a cool integration with the Maps technology, it can actually look at where that picture might have been taken without the metadata of the location. So that's just an example of using the API, applying machine learning into your application without any training. The natural language API, that's another thing. If you've got text data, you could use this. Here's an example, again, from the website, just putting in a news article. It will give you entities, so things like what are the objects in the text, what's the sentiment, the syntax, all that good stuff. And here we see classification, so taking different news articles and putting them into buckets. So what if you do have data? You could train a custom model, and that's what AutoML can help you with. So AutoML allows you, without code, to create your own custom model. So let's look at a couple examples of that. So say with vision, if you use our APIs, you're going to get labels back of what Google's categories are. But what if you have your own custom categories? So like here's an example in healthcare. Given different images, is this healthy or is this pneumonia? You would have to pass in your own labeled data to do that. Tables is a really cool new thing that we released a couple months ago. This works on tabular data. So you can basically give it your database information and give it a target column that you want to predict on, and it'll help you predict that. Pretty straightforward. A lot of data is in this format. You can take advantage of that. Natural language classification is another use case. So again, if you just kind of a fun example, you've got movies, movies. You want to get what category they're in, pass that in, you'll get a prediction. So that's all you need to know, right? Well, what's happening behind the scenes? So what's AutoML doing? It's using a neural network to do this, and in fact, it can ensemble all kinds of different types of approaches and kind of search across all the different architectures, find an optimal neural network or combination of approaches. So let's look back at classifying photos of cats and dogs. How does this really work? So you got a photo of a cat. Went a little fast here. And it's converting that into RGB values, so just a matrix of numbers. This is how the computer basically works. It's just math. It can look at the image. It can look at also things like maybe dimensions. Like here we have, the weight, the height, stuff like that, and plotting those and trying to find how do we group those into different buckets. So the neural network can help you do that. Neural networks basically are a signal processing system. It takes an input signal and it has different connections that can either amplify or weaken the signal across the network and eventually get to an output. And when you do training, you're basically looking at the error that you get when you make a prediction and then propagate that back through the network and adjust those weights and adjust the biases until you have a network that predicts very well. And typically, if you have multiple layers, you can get into more complex combinations of variables and features that aren't so obvious that probably humans wouldn't be able to figure out. So we talked about using AutoML and APIs, but what if you want to do something custom? That's where something like TensorFlow can come in. So you could, if you say want more control of your model architecture, you want to do advanced feature engineering, or you want to use some other techniques like unsupervised learning, where you don't have labeled data, you just want to see how do they cluster, or maybe reinforcement learning. So the Cloud AI platform is sort of the workbench that gives you all the different tools for custom AI development. It works with all kinds of different frameworks, and it gives you access to some pretty cool chipsets, so GPUs, of course, and then TPUs, or tensor processing units, that are super fast, that they can run through very large like image models, and are very cost effective. So that's something cool to check out. Models that might take a day to train might take minutes using TPUs. So it kind of got an all-in-one different set of serverless services for doing training and prediction. And then one thing to keep in mind in AI, and I could probably have a whole talk about that, is reproducibility of your models. It's one thing to create a model, but your model depends on a data pipeline. It has to be extracted in a certain way, clean, tests run on it. So the modeling is a small piece of the overall process. And so there are also data pipeline capabilities to make sure that when you run an experiment, it's consistent time after time again. Okay, so now we've gotten to the part where we're going to actually do a demo, and I have to do it in the back of the room, but just because the network, I guess, doesn't come up here. So I'll walk over there. Okay, so what we're seeing here is Google's public data sets. I did a workshop yesterday. We briefly talked about that. The public data sets are great examples like of large data sets covering all different kind of domains that you can use to experiment, maybe include in your models. Maybe you want to integrate economic data or weather data to make your models more accurate. You can access these on the Google Cloud. So my example of a model that might be a custom model is a time series prediction model. So something a little bit more complicated. So what we're going to do is look at crime data. There happens to be cities that publish their public data and put them here. So I'm going to look at Chicago actually has some of their data on here. So let's try to find that. All right, so we can see the public data set. I'm just going to zoom in a little bit so we have more detail. It discusses the data set, the terms of use, and all that. And we can go in and then view the data set, kind of find out more about the schema and how to use it. So here we go. And you can see a description of the data set. I'll kind of drill in a little bit to the table. And you can see details like, what each of the different fields are, and then a preview. So this raw data that we have is just a set of incident reports for 15 years from Chicago. So what I'm trying to do in this model is look at what are the trends, can we predict what the crime is going to be tomorrow, okay? So I'm going to need to do a little bit of pre-processing of the data, right? Each of these raw incidents isn't going to help me with that. So I've got a SQL query here where what it's really doing is just getting the counts of the crimes per day and then just sorting those. And so I'm doing this all in BigQuery. That's a SQL-like syntax. It's a data warehouse, gives you all this kind of fast querying capability. So here we go. You see at the bottom a bunch of rows. So you see starting in 2001 January with 1817 crimes and so on and so forth. So I could take that, I could export it and use it in my model. So now let's look at building a model. Okay, so I'm going to switch over to the AI platform. That's the workbench that we talked about for building your own models. And I'm going to go to my notebook server where I'm going to, so I already have one going here, where we can walk through a Jupyter notebook, which is kind of like a scratch pad for data scientists to try out things and run experiments. So briefly, I'm just going to show that what I'm doing is taking that raw data from BigQuery, importing a few packages. Again, the details of the code is really not the key thing, but I really want to show the concept here of how do you prototype and how do you create a custom model. I can go to BigQuery and I can load that data. Remember that SQL query that I just ran, pull that into a data frame that's the sort of typical data structure for data scientists. So you can see that same data that we saw in BigQuery I've got here into my model. And the first thing you want to do as a data scientist is really get to know your data, visualize it. So here I'm going to plot what the data looks like. So this is pretty interesting, a lot of seasonality in the data. We're seeing that over the summers every year it spikes and then it goes back down. You might even see some data quality issues. If you look at once a year, there's that sort of big spike, and that's January 1st. So it probably, to me, means that some of the record keeping isn't perfect and they just lump it into that year and they don't put an exact date on it. But what you're kind of seeing is it's going down over time and then it's been leveling off. Okay, so typically then the next step is pre-processing your data. Here I'm going to break it up into windows of 7 days. That's kind of what I'm going to use for prediction. So it's just going to I'll have a few helper functions here, and we'll move on to training the model. The model itself is very simple. This is something called an LSTM. That's a recurrent neural network, which all it really means is that it's a network that has memory. It's connected to itself. So it can kind of look backwards and make a prediction on a sequence of data, not just one data point. Okay, so I'm almost done here. Now we're going to go into the training. So I've just kind of not going to do a really, really extensive search. This is going to train really quickly here. If I wanted to get a more accurate model, I'd actually run this on some of those services that I just mentioned previously. Okay, so it actually is almost there. Oh, it looks like it finished. Let's go ahead and evaluate our model. Okay, it's looking like the standard error, it's off by about 75 incidents per day, which is pretty good considering that we were seeing that each day is about 1,000 or so. And let's plot to see how good it is at predicting here. Okay, so the orange is what it predicted. So really fit that line nicely. And the way that we did it, what you're seeing in the orange versus the blue is all the data. I took an 80-20 split where the 20% most recent data wasn't used to train the model. That was used to, the 80% was used to train. The rightmost 20% is my test data that the model never saw. And then what I did is I predicted based on that test data, and it fit the curve, which is great to see. So what you're seeing here is an example of building a custom model. I'm going to actually head back to the stage. So yeah, so we saw 3 different entry points with ML, right? So if you don't have data, you can use our APIs for vision, natural language. You can think about in mobile apps, web apps. There's all different. I want to be careful about that. Web apps, mobile apps. Just call the APIs, get a little more intelligence on your data. If you want to experiment with creating models and not do any coding, AutoML is a great thing to try. It also, even if, as an experienced data scientist, worth kind of trying AutoML, checking what you're doing versus what AutoML is telling you. Maybe it's finding something that you didn't think about. It kind of gives you a baseline when you're doing your own custom models. And finally, custom models, if you want to do the traditional data science where you really want to explore your data and create something custom. So hopefully after seeing that, you can have a picture for all the different tools that are out there and how to do some basic modeling. Any questions? Yeah, I'll start in the front. Yeah.
I saw that you guys had CPU. What is the difference?
Yeah, so GPUs are graphic processing units. We found that they do matrix multiply operations very well, and that's one of the key parts when you're doing a neural network. TPUs are even more specialized. So they're a chipset that's bad at general purpose stuff. They do one thing and one thing really well. They just do neural networks, because we were finding, like with Moore's law, that what's happening, this idea of computing power doubling every 18 months, is starting to level off. And so the thought was, how do you get to that next level of performance? You create these so-called domain-specific architectures, meaning you focus on what you're doing. So TPUs do some things like they can handle whole arrays, like matrices versus vectors that GPUs handle well. They're better with not writing to memory as they process the neural network. So basically, they're just a lot more optimized for neural networks, but they're kind of coupled with CPUs for other non-neural networks.
So I can choose either one platform?
Yeah, so you basically would say, okay, I need to run a job. Do I want to use a TPU, GPU, CPU? You can totally customize what you want to do. Yeah, I think you have the next question.
Yeah, so I know you gave us a brief demo, but can you maybe give us some thoughts as to what makes the Google platform better than, say, Amazon?
Well, yeah, I just want to more focus on what's great about Google. I mean, I would say that, Google brings years of great experience, research, a lot of fantastic engineers and researchers that are taking the learnings that we've had over the years and making them available to everybody. And believing in open source, a lot of things like TensorFlow, Kubeflow for doing MLOps, we're trying to give back and partner with the community on. Yeah.
You show recurrent neural network to process time series data. What other type of neural network would you recommend to handle time series data?
So the question was, we used a recurrent neural network to handle time series data. There are other techniques. So convolutional neural networks, it's traditionally been used for imaging, has been found to actually be really good for that as well. That's a little more complicated for a demo. And I think there's a session later in the afternoon kind of about traditional statistical techniques you can use as well. So there's lots of research on that. But I mean, RNNs are kind of the typical, like CNNs are for images, RNNs are for time series data, but that's starting to change and CNNs are being used. Yeah. Question? Yeah.
So there are many companies, including who come up with this OpenML platforms that make it possible to include multi-model machine learning and data science to create models and predictions. That necessarily creates the danger of potentially more models. Have you thought about it, maybe address it in some kind of way, education, or otherwise, what do you think?
Yeah, I think that's a great question. The question was, now that we're making AutoML, democratizing AI, making it available to everybody, is there a risk that we could be, that in the wrong hands, or if people don't have the right skills, they may be making mistakes? And certainly, and I think this kind of just reinforces that data scientists should not be afraid of AutoML. Data scientists should look at it as another tool in the tool belt, just like doctors can leverage, nanosurgery, or all these other cool tools that are at their disposal. So I think AutoML still requires, a team of experienced data scientists that know why decisions are being made. It just enables you to move faster and expands the pool of people that can contribute.
So one of the challenges that we face now for that, there are a lot of data scientists, and data scientists have different tools which they use to work. Some data scientists use R, some use Python, some use Spark and Python. And there are different serialization techniques for each type of language. So Python is Python filling, with TensorFlow, TensorFlow serving. So how do you manage to handle like a variety of different languages and frameworks and be able to serialize them and then containerize them for deployment using the platform?
Right. So the question is, there are a lot of different languages and tools, frameworks, and what glues them together, I guess. I can say that the Google Cloud Platform has specific like VM images that have all the R tools installed in Python. One of the things that I didn't show today, because this was a quick overview, was Kubeflow, which enables containers to run different custom steps of a pipeline. And something like that can be very helpful because there's a concept of model management. I talked a little bit about, tracking your models, having history. Creating a model, checking accuracy is one thing. It's another thing to put in production, have multiple teams in a larger organization kind of like manage its life cycle. So, tools are part of it, but I think part of it is data science needs to continue to evolve, just like software engineering, to have best practices, DevOps, things like that to make sure it stays on track. And how are we on time? Okay, all right. Well, maybe one more question. In the back, yeah.
I'm in academics, and so I teach a lot of students, so we're getting into data science. Are there packages like for students so that maybe discounted rates or for classes that are teaching data science to students, and they're going to use more than the 12 free, whatever, the free trial version to teach?
Yeah, so the question was for education, are there any tools and things? There's a ton, off the top of my head, maybe I don't have great answers on that, but I do know that, we have a lot of things like something called quick labs where they're, free labs that have sort of credit sort of built in, so you don't have to pay anything. You can sort of it'll spin up a server, you can run a lab, and then it'll shut it down. That's Quick Lab with a Q, if you want to Google that. We're really putting a lot into the education and making it easy for everybody to use. So, all right, thank you very much.